Good day, grade 12. In this video, we are going to calculate the equilibrium constant. So, the question reads as follows. Consider the reaction represented by the balanced equation below. This is the balance equation that they're talking about. And you can see we have gas, and also gas here. So, in other words, we don't have liquid, we don't have solid in this case, and we know that when we calculate Kc, we focus on the concentration that are meant for gases, not liquid and not solid. So we are also told that initially 2 moles of NO2 in gases and also 2 moles of SO2, that is in gases also, were mixed in a sealed 2 decimeter cube container. When equilibrium is reached at 700 degrees Celsius, there are 60 grams of SO3 present in the container. So now the first question reads as follows. Define the term chemical equilibrium. So if you check it out, the chemical equilibrium, it's where the rate of the forward reaction is equal to the rate of the reverse reaction. Because even if you check the word equilibrium, the equi here it just simply means that we are talking about something that is of equal nature. And what is it that is equal when we talk about chemical equilibrium is the rate of forward reaction being equal to the rate of the reverse reaction. So that's how you must define it. You must be able to tell that we are talking about a situation whereby the rate of the forward reaction is equal to the rate of the reverse reaction, like that. Now, the second part has to do with calculating the value of equilibrium constant for this reaction. So we are going to use the given information to calculate the equilibrium constant. So the first thing that we can do, we can draw our table nicely so that we can fill in the given values. So the values that I were given were number of moles and also the mass of the SO3 that is present when equilibrium is reached, like that. So let's use this information and substitute the numerical value that we know. The first thing that we can do, we can rewrite this equation here on the table. So here it is. We have NO2, which is a reactant, which is this one, followed by SO2, which is this one, it's also a reactant. And then on the product we have SO3, which is this one, and NO, which is this one. So let's look at the information that is given. We are told that we have 2 moles of NO2. So this is initially. So we have 2 moles of NO2. Where is NO2? Here it is. So it simply means that we are going to write underneath here on initial, which is mole. I wrote this MOLA to indicate the moles because we are talking about number of moles. So this means here I will write this 2 for NO2 because the value that I'm going to write here, all these values that are meant to be right here related to NO2. So initially we have 2, so I will write it here like this, followed by what? By 2 moles of SO2. Where is SO2? Is still a reactant. This is SO2 here. So I'm going to write again that 2 here. And then from there, what else must I write? I will write 0 here, 0 moles here for SO3, and also 0 mole for NO. Why do I write 0, 0? It's because initially, when we started our reaction, we don't have product. So as such, we can write 0 and 0 here because we didn't have product when we started our reaction or this reaction. We only have these 2 moles of NO2 and 2 moles of SO2, like that. Now What else is it given? We are also told that at equilibrium, when the equilibrium is reached, we are also told that we have 60 gram of SO3. Where is SO3? It's one of the product here. So we can now find the number of moles, because why should we have to find the number of mole? If we check this table out, at equilibrium we have number of mole here, we have number of mole here, the change in number of mole. Initially we also have the number of mole. So that's why we it's important for us to change this SO3 and convert it to gas mole. So in other words, we want to calculate the gas mole of SO3 like that. Let's do that quickly. You are more than welcome to pause the video and work it out. From there you will come and see how did I work it out. So small letter n meant for number of moles equal to small letter m divided by capital letter M, whereby this capital letter M is the molar mass. We normally got the molar mass from the periodic table. So from there, if we were to substitute, the mass is 60 gram. We are told that this mass is 60 gram, mass of SO3. However, we will need the molar mass of SO3, meaning that we are going to a periodic table and find the mass of sulfur, we find the mass of oxygen. However, if you check it out, we have 1 sulfur and 3 oxygen. It simply means that we have to find the mass, the molar mass of 3 oxygen, not 1, because we have 3 of them. So this is how you can do it. We have 32.07 gram per mole, which is the mass of sulfur, and then 3 multiplied by 16 gram per mole. Remember, each oxygen has 16 gram per mole. So the molar mass of each oxygen is 16 gram per mole, meaning that 3 of them will contribute 48 gram per mole. So the total molar mass of SO3 will now become 80.07 gram per mole. So allow me to write it as 80 gram per mole. However, you're also more than welcome to write it as 80.07. In actual fact, it's best to write it as 80.07. From there, you will just press a calculator, then the answer becomes 0.75 mole. However, you were told that this 0.75, since this mass is it's obtained when equilibrium is reached, it simply means that you are going to write the number of mole at equilibrium, not here at change. Meaning what? It's SO3. Here it is, meaning that the value you are going to write it here, because this is where you're supposed to write the number of moles for equilibrium, or that way we obtain at when equilibrium is reached. So I will come and write that 0.75 moles here. Now, since we are talking about the product, it simply means that the change in number of mole is still going to be 0.75. So this is the change in number of mole. From there, this number of mole that we have here, since we are talking about the change in number of mole, we can use mole ratio to find the number of mole of this one here and this one, and also this NO here. So we are going to use mole ratio. However, if you check our equation out, the mole ratio is just 1:1, 1:1, meaning that the number of moles are going to be equal for all reactants and all the products, since the mole ratio is 1:1. Now, this simply means that the number of mole for NO is going to be equal to the number of mole of SO3, which is going to be 0.75. This is going to be applicable even for SO2. So the number of mole is going to be 0.75. Why? Because the mole ratio is 1:1 throughout the whole equation, like that. So from there, we can now say we started with 2, and then the changes of number of mole was 0.75. Then what will be the leftover is just a matter of you pressing the calculator and say 2 minus 0.75, which is the change in the number of mole. Then the answer will become 1.25. Same applies to this one. We are going to say 2 minus 0.75, then the answer will become 1.25. 0.25 like that. Same applies to this one. We started with 0, then the change in number of mole was 0.75, meaning that even here at equilibrium, the change that we brought about this reaction as far as the number of mole is concerned on the product is going to be 0.75. Now, when we calculate the equilibrium constant, we from the expression, from the definition, we write the KCS, or we express KCS, the concentration of the product, divided by the concentration of the reactant. And if you check this information here, this is not the concentration, instead is the number of mole. So we are forced to convert all this number of moles that were obtained at equilibrium, and we convert them to the concentration. How do we convert number of mole to concentration? Number of mole is equals to CV, whereby C is the concentration, V is the full volume. This will simply means that the concentration is going to be number of mole divided by V, whereby V is the concentration. So meaning that we are just going to divide every number of mole here by the volume, and the volume is what? Is 2 decimeter cube. So we'll say 1.25 divided by this volume, which is 2, the answer become 0.625. We said to this one again, we're going to say 1.25 divided by 2. Where are we getting this 2? This is the 2, which is the volume here. So the answer become 0.625 again. From there, we come here and say, 0.75 divided by 2. The answer become 0.375 like that. Same applies here. The answer is going to be 0.375 like that. So if you check this one out, this is the concentrations, and we can now substitute these values to find the equilibrium constant. So this is how we are going to substitute and find the correct answer like that. So if you check it out, SO3 and NO2 should be the product. If you check even on our reactant, we have SO3 and NO2 on the product. Product are written on the right hand side, then the reactant are written on the left hand side. So these two, if you check them out, they are on top. It should be like that. Then the NO2 and SO2 should be the reactant. It should be underneath NO2, SO2. So it's just a matter of substituting this. So these two, 0.625, 0.625 are written underneath because they are the reactant, and here are they underneath here. From there, 0.375 and 0.375 are the product. They are written on top. Then you press a calculator and you find the answer being 0.36 like that, with no units because KC doesn't have a unit. So thank you so much. If you find this video useful, please kindly give a thumb up. Thank you.